Hey folks, Todd Coburn here with the Aerospace Structure series. This little video is going to look at particles and how we evaluate the forces on them. Let's start by looking at an aircraft. Now, an aircraft is a rather large thing, but actually, when we talk about particles in rigid bodies, this has more to do with the way that we're going to pretend that the item behaves rather than the way it actually behaves. So we can treat an aircraft like a rigid body where we can evaluate forces on it and where they're located along the aircraft, or we can treat it like a particle, which is kind of like we take that whole aircraft and squish it down into just a little infinitesimal point. And then all the external forces acting on that aircraft, we can evaluate how those behaves. Now, while this may seem like complete nonsense, it actually is a very practical means of evaluating the major contributors to how the aircraft behaves. And it is a tool to do some amazing pieces of analysis for aircraft. So, one of the first idealizations we will often make is to treat that aircraft like a particle, look at all the external forces and see how it behaves. Later, we can take what we've learned from that, often looking at the kinematics and kinetics, which we'll study in our dynamics class. And then we can go and look at this as a rigid body, meaning where those loads are applied, and look at all the internal forces and bending moments and things like that, which we'll learn about later in this statics sequence. So let's just take a look at our aircraft, and let's say that that aircraft is flying along at level horizontal flight. Now, if that were happening, that would mean all of the forces must be in balance. We will learn in dynamics that if there's an imbalance of force, we're going to get acceleration. To have a non-acceleration, we will need to have a balanced set of forces. And this is true for a lot of actual moving things. For example, this aircraft, if it had 50,000 pounds of thrust acting on it, which means pushing it along, if it's flying at level horizontal flight, that means it also has 50,000 pounds of drag. Any aircraft flying at level horizontal flight, which means the speed is not changing, will have the same drag force as it has thrust force. These have to be perfectly balanced, because if they weren't, that would not be going along at a constant velocity. It would be accelerating. So horizontal flight, the drag is equal to the thrust. We see the thrust here on the back end of the plane, pushing it forward, and the drag resisting that. At the same way, if this is an aircraft, it's up in the air, that means that aircraft has weight, and that weight is perfectly balanced by the lift. So we see any aircraft that is flying at a horizontal constant velocity, if it's constant velocity, the thrust is going to perfectly be resisted by the drag. The sum of forces is zero in the horizontal direction. Therefore, it is either at rest, which wouldn't be up in the air, or it's moving at constant velocity, which is our case. Meanwhile, all the weight, in this case, we have a 75,000 pound plane. If we are at constant elevation, that means we're not accelerating upwards or downwards. That means that the weight is perfectly balanced by the lift on the wings. So we have 75,000 pounds of lift, 75,000 pounds of weight. That sum of those equals to zero. Therefore, this thing stays at level. And because we have thrust matching our drag, we stay at constant velocity. So this 75,000 pound plane is flying at level horizontal flight because the lift is perfectly balancing the weight and the thrust is perfectly balanced by the drag. Now, if you were to speed up, we'll learn about this in dynamics, then you would need to apply more thrust to overcome the drag, but the drag is going to increase also, so you would get an acceleration until the drag balances that thrust. We'll learn about that in dynamics. What we need to understand right at this moment is we're treating this aircraft like a particle, and the sum of forces must be zero. We can sum our forces in any direction. This is called an imposing equilibrium. We can draw a free body diagram. We shorten that FBD, free body diagram. A free body diagram has all of the items that we're going to evaluate, any pertinent dimensions that are needed, and the forces that are applied, every force acting on the item. In this case, we've got an aircraft. We're treating it like a particle, and we can see that we have all forces. We have vertical forces, all vertical forces, and all horizontal forces, and you'll notice they perfectly balance. They must balance due to Newton's laws, and if they completely balance, then we will have a static problem where nothing's moving. That's the whole study of statics. We'll be evaluating that kind of case. And if there is an imbalance, we still will get equilibrium because we can use that acceleration vector as an inertial vector, which when we complete that, adding that into our system, we now can get what's called dynamic equilibrium. Right now we're in statics class, so we can just focus on the forces, treating everything like it's static, even if it's not. We can pretend it is and actually gain some very meaningful pieces of engineering. So this particular aircraft, 75,000 pounds with a 50,000 pound thrust. It must have 75,000 pounds of lift to hold that horizontal, the same vertical position, and it's going to be experiencing 50,000 pounds of drag in order to stay at constant uniform velocity. Because if there was ever an imbalance in our lift forces, we would be accelerating up or down. An imbalance in our thrust versus drag forces, and we would either be speeding up or slowing down. All of those are cases that we might want to evaluate, but we won't do those till we get to dynamics. Right now we're looking at a balanced static case. When we impose equilibrium, what we're doing is recognizing that all forces must be completely balanced. So we can sum our forces in the vertical direction, and they will have to be zero. You can see summing 75 minus 75,000 is zero. Therefore, we're in vertical equilibrium. And if we sum our forces in the x direction, we have 50,000 pounds minus 50,000 pounds equals zero. We're in equilibrium there. This is the way we're going to impose equilibrium throughout this entire sequence of topics as we study statics. Let's take this a bit further and look at a slightly different aircraft in horizontal flight. Let's say we have 50,000 pounds of thrust, which is perfectly balanced by 50,000 pounds of drag. Now let's say our new aircraft weighs 60,000 pounds, and we want to find out how much lift do we need to hold horizontal flight. Well, we can now just sum our forces. We'll sum our vertical forces. The sum of the forces must be equal to zero. So the best way to do this is sketch this just like I'm showing you here. You can see we've got the sum of the forces, sum of the F. You see that? We're going to show the direction. We're summing them in the Y direction. And to make that clear, we're going to put a little vertical arrow, and usually we'll put a little plus sign next to it. So the sum of the forces upwards, we got the arrow and the Fy. Fy means we're summing vertical forces, and the little arrow shows what we're calling positive. They have to equal zero. That's called imposing equilibrium. Now we can write all forces that happen to be vertical in direction, sum those up to find out any unknowns. So we have the lift, which is acting in the positive assumed direction, minus that weight of the aircraft, which in this case is 60,000 pounds. We solve this system of equations, and we find out that our force is 60,000 pounds. So if we sum those L minus 60,000 equals 0. Solve the algebraic equation. We find out the lift is 60,000 pounds. It would also be good to put a little arrow upwards next to the 60,000 pounds to make it clear about direction. Let's look at another idea. Let's say we have an aircraft and it has 40,000 pounds of drag. How much thrust do we need to have a constant velocity aircraft? If the aircraft is flying at a constant velocity, how much thrust do we have? For this problem, all we need to do is sum our horizontal forces. Sum of the forces in the positive, we're showing a little arrow showing positive, and we're putting a little plus sign to emphasize that that's our assumed positive direction. We could have assumed left is positive, we could have assumed right is positive, but we should show whatever it is we're assuming. That's what we do here. Sum of the forces in the positive x direction equals 0. We now insert the values. 40,000 minus t equals 0. Okay, solve the algebraic equation, and we find out that t is simply 40,000 pounds. We box our answer. What would be good here that I didn't sketch is also show direction to make it clear. Now in this case, the arrow of t shows that it's acting to the left, so we're just showing the magnitude. But what's even better is to have a little arrow right after the 40,000 showing the direction that thrust is acting. Let's look at another example. Let's say we have a 35,000 pound weight. Our aircraft weighs 35,000 pounds. And if it is flying horizontally, that means the lift must equal the weight. So we sketch our little lift arrow, and let's say that that's an unknown. We now can solve that by summing our vertical forces. The sum of the forces, you'll notice we have the summation sign, that's the sigma, F in the y direction, which means we're summing in the vertical direction. To the left of all that, we're showing what we're calling positive by indicating a plus sign and a vector showing what we're calling positive. And we're completing the equation to show that these must equal to 0. We now can insert our variables. L minus the 35,000 equals 0. Solve the equation, and you can see that we find that L is 35,000 pounds in the vertical direction. We're showing the magnitude, we're showing a vector showing direction. Okay, now let's look at a particle. Let's say we just have a little particle in space, and it's subjected to some forces. Let's say we have, say 10 kips upwards and 20 kips to the left. And we also have P1 and P2, which are unknowns. Well, if this is a statics problem, this needs to be in equilibrium. We can determine what our two unknowns are. Now, this is actually obvious by inspection what these values are. However, let's practice imposing equilibrium and solving the system of equations. We can start by summing our forces in the x direction. Remember, we have the summation sign, that's sigma. We're showing what we're summing. We're showing forces, so we're going to use a capital F. Those forces are in the x direction, horizontal direction, and we're showing the positive direction by putting a little vector to the right and a positive sign next to it, which says that's what our positive is. Imposing equilibrium means these must sum up to 0, so we say equals 0. We now insert our values. P1 is in the positive assumed direction. That force is 20 kips is in the negative assumed direction, and those must be 0. We now solve the system equation, and the equation, and we find that P1 is just 20 kips. What we want to do is show magnitude and direction, so it's 20 kips with proper significant figures. We show the direction, which is acting as shown with that little arrow, and we box that puppy to show that that is our answer if this is a school kind of problem. Or even if this is a significant problem for an industry analysis, you might want to offset it from the other analysis. We then can check what the vertical value is by summing forces in the y direction. Once again, we have the summation sign. We're summing forces in the y direction. We're showing positive is upward. Those must equal to 0. Now we insert values. We've got 10,000 kips upwards, and we've got P2 acting downward, and we find that P2 is just 10,000 kips. And we show positive with a vector pointing in the direction. That's 10 kips acting downward. We show so you can see here we have identified our value, P2. We're showing the magnitude with proper sig figs. That's 10.00 kips or 1,000 pounds. And that's acting in the positive, or excuse me, it's acting in the downward direction. That answer is clear, concise, and correct. So this is how we evaluate particles. These are just a couple simple problems to help us hone our skills at evaluating particles. Enjoy.